Hello, my name is Gergely Tokács, and my co-authors and I are from the Slovak University of Technology in Bratislava, Slovakia, and we're presenting our paper titled MotoShield, an open, miniaturized DC motor hardware prototype for control education. Future control engineering professionals require extensive training, and of course this is true for any other field of engineering. Simulation examples or numerical exercises alone are just not enough. That is why we are taking our students to laboratories to let them experience some practical problems using laboratory scale experiments, trainers, and other didactic devices. The ongoing pandemic has forced us to use simulations and numerical exercises instead of laboratory exercises, and has also demonstrated the value of the so-called take-home experiments, in which didactic devices can be loaned to students for homework, assignment, and projects. One of the typical exercises in control engineering is the speed control of a direct current DC motor. These examples can be found throughout the internet, both in their numerical form and also some practical examples. Our paper discusses this fundamental control engineering example. How can one turn a numerical exercise into something more lasting and practical? Well, several vendors offer ready-made, off-the-shelf training devices with a simple DC motor and a connection to a computer. However, these devices tend to be quite expensive, large, heavy, and delicate. So, educators are reluctant to lend them out to students for homework assignments or other projects. Another way to realize these experiments is by using improvised devices. Control engineering laboratories around the world are filled with DC motor control experiments of various sophistications. Some instructors even ask their students to complete the circuit by themselves. This, of course, has its advantages, such as a cheap price and, of course, the learning experience when one builds the device itself. However, the disadvantages are that these devices are fragile and they are unique to a laboratory, group, or school. Therefore, the learning materials are not portable. My co-authors and I have looked whether there is a middle ground between buying a commercial device and building your very own improvised one. We looked to the Arduino initiative for an inspiration. As many of you already know, Arduinos are small microcontroller prototyping platforms that are today widely used by hobbyists, schools, and even university engineering courses. These devices are cheap, open source, easy to buy, and essentially standardized. They come with their free integrated development environment and have a great community and an abundance of learning materials. What is more important for us now is that they are cross-compatible and they can be easily expanded by additional hardware by the so-called shield system. The Arduino baseboard gets a printed circuit board connected by header pins, and so the microcontroller has now additional functions. These boards can be removed and swapped for other functions. Some of them are, for example, Wi-Fi or Ethernet. Based on this, we have established the AutomationShield initiative, which creates novel tools for control engineering and mechatronics education by implementing a laboratory experiment onto a single Arduino expansion shield, and thus essentially creating a tiny control or mechatronics laboratory which fits in the palm of your hand. This little laboratory should be then cheap, open source, possible to build at home even by beginners, fairly standardized, and should come with a free software library that is compatible to the Arduino IDE. One of the results of the AutomationShield initiative is the so-called MotoShield, which is an early hardware prototype of a DC motor control experiment. The MotoShield is then essentially a laboratory in the palm of your hand. It's very small and can be taken home and lended to students because it's also very cheap. The MotoShield just contains a DC motor with an incremental reader to get a feedback of the position and the speed of the motor, a DC motor gear, some power electronics and electronics to measure the current passing through the motor for modeling purposes. As I have already remarked, the device is open source. That means that anyone can download the editable schematic files of the electronic design along with the printed circuit board layout and also a format that is ready for manufacturing. Thus, students or educators can send these files to a manufacturer and get the circuit board back in a couple of days for very little money. In addition to the circuit design and the PCB manufacturing files, we provide a bill of materials containing each component that is necessary to finish and assemble a single device. These components are easily obtainable, globally sourced, there is nothing exotic, and the total price adds up, including the manufacturing of the PCB, to a total of 22 US dollars. So this is a truly low cost hardware. Even disposable, so it can be lent for homeworks and other sorts of projects. The MotoShield and the AutomationShield initiative is not just about hardware. We also provide a free and open source application programming interface API written in C++ for the Arduino IDE. This is a part of the AutomationShield library. The point of this API is to simplify and abstract some of the low-level hardware functions so that students or instructors can move on and write their very own control engineering applications right away. For example, to initialize the hardware, one just needs to call the begin function from the MotoShield object. To calibrate the speed limits, one calls the calibration method. To read the motor speed in percent or in revolutions per minute, one uses the sensor read method. Or to send a certain power to the DC motor in percents of the PWM signal, one uses the actuator write method. Or, for example, to read the external manual reference into a variable R, one needs to call the reference read method. We have created a version of this API for the high-level scripting language MATLAB. The two APIs are essentially the same. They use the same syntax so that students can switch quickly between the two environments. The API also exists for Simulink as a form of collection of blocks that can be combined by the standard offering of MATLAB, creating highly powerful and complex real-time applications for the microcontroller. Other than the APIs, the AutomationShield library also contains typical classroom examples, such as the PID control of motor speed. The examples are well commented, and students can look at the results of their feedback control right in the Arduino API without using any external tools such as oscilloscopes or laboratory measurement cards. These examples are available across the currently supported environments such as Arduino IDE, MATLAB, and Simulink. Another good example suitable for teaching is system identification of the underlying dynamics going on in the DC motor, which begins with first principles modeling and mathematical physical analysis. Then students can move on to data acquisition and system identification. And finally, they can compare their results with the measurements. In the simple PID control loop shown on the slide, the device is represented by a single block from the AutomationShield library, and the rest of the algorithmic blocks are a part of the standard installation of Simulink. As you can see, students can quickly implement their own feedback control solutions and auto-generate the C code and executables from Simulink and deploy them to the microcontroller while still being able to view the process in real time. So this is essentially what we present in our current paper about the MotoShield. Before I would wrap this presentation up, I would like to take the opportunity to remind you that there are several other similar devices already described in the open academic literature and on our website. These devices are also extremely small and come in a form factor of an Arduino shield. Some of these experiments realize magnetic levitation, such as the MagnetoShield, air flotation of a ball by the float shield, the famous ball on beam experiment by the Bob shield, or the rotational flexible link by the link shield. You're welcome to check these devices out in our papers or at our website. That is all for now. I would like to thank you very much for your attention, for watching this video presentation. And if you have any questions, please feel free to contact me via email or have a look at my website or social media profiles. Bye bye.